Thank you very much for coming, and thank you for the invitations. And it's my honor to be here and give it this distinguished lecture series in Bose Institute. So I was really impressed in the past 2 days, the visit here and this exciting research going on, as well as the facilities and people here. I think it is very impressive in many aspects. Originally, when I was invited to give a talk, that I didn't give a talk titles until quite recently, but then I found that somebody put my talk title already. And the title that are listed here, that as well as you can find the poster, is actually the title that I didn't give. I don't know, somebody actually assigned to me. But then I just reassigned my talk title as a bit more some of the research that related to my research. But then actually, the reason that I just bring it back again here is, in past 2 days at my experience here, I start to realize that a lot of things in this title is pretty much a generic title that also related with something going on this research center, that whether I want to kind of make a little bit of pitch onto the my research, which is a two-dimensional systems tied with this quantum frontier and at the nanoscale. So we'll see how it goes. All right, so as the title says, that the main topic that I want to discuss is about the particular class of material that I've been working on. It's called the two-dimensional material, or the van der Waals material system. And it's a material that we've been known for quite a long time. Nature provides us a lot of so-called layered materials. Graphite is a good example. In this material, that the chemical bond is within atomic layer. But between the layer, there is no real chemical bonding. It's just weak van der Waals hold them together. Because of this weak van der Waals force nature, the first thing you can realize is many of this material that simply can cleave quite well using Scotch tape that people in about 12 years ago demonstrate you can break the graphite down to a single layer of the atomic layer of graphite, what we call the graphene. And that is possible simply because the material is stable because all the chemical bond is within the layer. It turns out that's only the beginning, and soon we start to realize there are all other type of the so-called layered materials, or we can call the van der Waals materials, that you can in principle take this material down to one monoatomic layer, or in other words, you can also grow this material using CVD, MB, and various different type of synthesized method. You can grow this material stabilized down to one monoatomic layer such that you can effectively create a two-dimensional material system. And that has been quite exciting. First of all, the material comes with a various different flavor. Graphite that I mentioned that turn into the graphene, but if you just go above this, down below the periodic table, there's silicene, germanines, and all this. The number 4 families can generate something like graphene, like the structures. They can be stabilized down to monoatomic layer, and they tend to usually shows the interesting electronic properties, so-called semi-metal or zero-gap semiconductor or Dirac materials in modern terms. But also, some of the material becomes insulator. Boron nitride that I'm going to discuss is a good example. Or some of the materials, especially transition metal dichalcogenide, which consists of the transition metal with chalcogen atoms such as sulfur, selenium, and tellurium. Those kind of materials often demonstrate as a semiconductor PON type, or sometimes it becomes superconductor if you just use an niobium, for example, or some materials becomes the strange metal such as charge and wave system. And the list actually grows every day, and we've been just enjoying to see in past 5 or 10 years that what kind of materials we can create in the two-dimensional limits. And one can study a lot of their interesting electronic property in this, in a sense, quantum limits of this two-dimensional system. Now, another advantage we can see is in this that captured in this cartoon which was released by the Physics Today last year. It's kind of following term. Not only you can study them as down to monoatomic layer limits, such that you can understand their interest in quantum physics. In principle, you can stack them together. This is relatively easy in part because, again, it's a weak van der Waals force. When you just put them together, you don't have to worry about their lattice mismatch and just commensurabilities. They simply just kind of put them together, and because of van der Waals interaction, they just can hold them together, and yet there's no real chemical bond, so they just kind of exist as this stacked system. So this immediately allows us to do the following things. Not only you just kind of work on single layer system, you can just bring it back and stack them together to put some of these complicated structures, either in plane or even out of plane. Either out of plane, but even just in plane. Even further, because as I said, this material comes with a various different flavor. You can think about this as a units that just display some of the interesting functionalities, right? So if you just choose by just interesting design, like as if you just block the kind of stack this Lego block, in principle you can stack these van der Waals materials to try to come up with quasi three-dimensional structures with some of the interesting the functionality. Basically, this idea of a heterostructuring of this functioning system actually bring us a quite exciting new moments, such that we can probably study these materials down to atomic length scale and look at this how the quantum mechanics plays a role. But on the top of that, one can actually build this into some of the functional devices, where not even individual layers that the properties that appearing in the interface actually exceed our expectations coming from just looking at individual materials, right? It's not only just kind of science fictions, but indeed in past 5 years, people have been moving on to demonstrate some of the devices, starting from the simple field effect transistors or interconnect or biosensors, the tunneling device, memories, LEDs, and kind of more of this electronic and optoelectronic devices based on this combination of 2D materials, and even just try to build up these flexible devices. There are lists actually growing up, and a lot of the interest to use this material as some of the application has been come around in quite recent years. I'm not going to discuss about the detail about the applications simply because I'm not good at this kind of real applications, but at least I want to kind of address a part that what kind of the capability that we've been started kind of developing, and moreover, what type of the interesting the physical property we start to see, especially electronic and electro-optical properties that might be useful for some of this realizing conventional device, I would say, but even further beyond this conventional device where the quantum mechanics plays quite an important role. The method that we've been using is a rather simple thing. So it's basically what we call the van der Waals heterostructuring. This method has been developed out of the collaboration that I had at Columbia University a few years ago, especially together with the Jim Horn's group at the Mechanical Engineering. But this can be easily generalized quite a bit. So of course, you can get this, the materials using various synthesis methods, including the heterostructures, such as MBA, MOCVD is a method that people trying. But even before that, if you are not worrying about the scaling up of the idea, following idea works quite well. So I told you that we can cleave this material down to single atomic layer on the surface, say silicon oxide surface or something. And then you can prepare the polymer tapes or polymer, the membrane, specially designed such that it may not leave a lot of residues, and we can control the adhesions. And then you start with pick up some of the van der Waals system you want to start with. Typically, boron nitride is a good system because it is a good insulator. And then you bring down this boron nitride onto the single layer system, in this particular case, the graphene. And you just kind of changing the temperature of substrate, controlling the adhesions between the silicon oxide to this material and material to this boron nitride. You can controllably pick up these materials, say from the silicon oxide, and attach them in the boron nitride, right? And then you can start to repeat this process and over again. And other materials, in this case, you can pick up the boron nitride again or other the layered materials. And then in the end of the day, you have this stacks of the materials with the different compositions in there. Now, it depends on the sequences, you have the different type of things. But the important part is, if you just do it in really controllable way, as you see in this cross-sectional TM image, here is graphene encapsulate between the boron nitride. Important part is that this interface, especially this hetero interface between graphene and boron nitride, is extremely clean. There's no single atomic defects you can see in this cross-sectional TM images. All this dirt and impurities basically squeezed out from this van der Waals interface, such that you have atomically sharp interfaces possible. Not only you can get this MB type of this clean interface, in principle, you can just kind of cut this the stacks that very careful manner and expose certain atomic layer that you want to make the contact. And there has been some method developed that you can selectively contact the layers that you want. In this particular case, graphene is contact with this gold and make the extremely good contact such that you can make this device that based on this the quantum structures where individual atomic layer can be contact, right? So that's very important part. So in a sense, you can mimic that semiconductor heterostructures people have been synthesized using MB technique, but here there's a poor man's MB technique, but nevertheless, it works rather beautifully, especially in the graphene. Now we can make this type of devices, such a clean limit. The electron mean free path measured in this type of the system is basically exceeding several tens of micron. In fact, that electron mean free path is set by the size of sample we can get, at least in the low temperature, means that we can make extremely clean interface between graphene and boron nitride. This type of the clean sample immediately allows us to do a lot of exciting physics. This is a good example that once you apply this strong magnetic field, you start to see that your transport shows this quantizing effect, what you call often the quantum Hall effect. But it's not only quantum Hall effect. It turns out there's an interesting interaction between the graphene and boron nitride, what you call the Moire pattern forms, and give us the superlattice, which actually quantize the graphene band even further and create all these kind of complicated structures. I'm not going to discuss anything in detail here on this one because it's a little bit esoteric subject. But nevertheless, this problem actually gives us exciting this new physics that how this the commensuration or incommensuration lattice structures interact with the magnetic field to create this fractal like the energy spectrum in the system. And this type of experiment is only possible that when you have the extremely clean sample that are available in the extreme quantum condition. So this is a good example that what you can do when we have this clean sample. But this is the beginning. It's not only graphene, but you can make all these heterostructures in various semiconductors and the other system. In this particular example, we have the boron nitride graphene and molybdenum disulfide is encapsulated in between boron nitride, make the heterostructures. That graphene onto the molybdenum disulfide make the good contact between them. So graphite in this few layer of the graphene serve as a good contact on molybdenum disulfide, and nevertheless, molybdenum disulfide is encapsulated in this boron nitride, give us a really good channel, and entire these structures can be worked as transistors, and their mobility is quite good, something like easily 10,000s. Under the magnetic field, they shows again quantum oscillation. So you start to see that this example actually extended beyond the graphene. One can make this kind of interesting, these quantum devices as well. Not only just kind of this magnetic field and low temperature quantum device, but you can also make some of this known, the other quantum device beyond the CMOS. Here is another good example. In this particular example, we have, sorry about this small characters, but here is the tungsten diselenide, P-type semiconductor, and another tungsten diselenide, but in between that we insert a very thin layer of the boron nitride as a tunneling layer, right? Again, this made out of this successive stacking. And then you can clearly see that between these two layers, because it's a so thin boron nitride, is a good tunneling device. Now, this type of the tunneling device is what we can make with the so-called quantum well resonance tunneling device that out of semiconductor heterostructures. Big difference here is we have the gate from top and bottom such that we can control this band alignment between these two materials, right? In the net, when you measure tunneling current through this device, the tunneling current at the fixed gate voltage, for example, shows increasing tunneling the current as a bias voltage, and there's a peaks and there's dips and going up again. So this peak appears in the terms of the bias is what you call this the negative differential resistance. In a sense, there's a negative slope in here. It's actually indications of this resonance tunneling between these two-dimensional system. So it has been demonstrated again say many of these quantum heterostructures. Asahi diode is a good example. But the important part is those kind of the signature of the resonance tunneling peaks can be movable by the gate voltage we apply in the system, showing that we have the complete controllability in those kind of heterostructures, and we can build up this type of interesting devices as well. So not only this type of the electronic device, it turns out you can also turn this into optoelectronic devices. In this particular example that we have P-type or N-type semiconductor. We just put them together again in very similar fashions. And you can see that this is the thinnest PN diode you can make. Either P or N junction is only 1 atom thick materials. But the exciting part is when you just bias this one, you start kind of illuminating the light like this, the LED, light emitting diode. And that the spectrum can be tunable by the gate voltage again, simply because we can tune this band alignment, right? Or if you want, you can use it as these photo sensors. If you shine the lights and measure the current, you get the photo currents actually is different. It's a kind of, you can view as world thinnest photovoltaic diode. But this type of the device operation can be done in the extreme, that when you make this sample is extremely thin, right? So this is kind of good starting point that what kind of the application we can just kind of launch on this extreme to the limit of the system. Now, I know that up to here, that is a good demonstration, but probably a lot of my physics colleagues may not be too happy to see this. Well, this is electrical engineering again. I know that you can just make it thin, but what we can learn from here. Now, exciting part of this two-dimensional system and the heterostructure is actually allows us some things to go beyond what I just kind of showed you as an example of the conventional electronic device we've been known, right? So let me just show you a few examples that I'm pretty much excited about the opportunities. It's by far it's an ongoing project, but nevertheless, you will see some flavor of what we are excited about just kind of using this type of 2D system. So you've been heard about, especially in this institute, you've been heard about a lot of this Majorana fermions and quantum computing based on the Majorana fermions, Majorana particles, and so on, right? So I don't have to explain a lot of these things, but in 1930s, this Ettore Majorana, the Italian physicist, come up with this intriguing solution of the Dirac equations, which is brand new equations to describe the electrode, the relativist quantum mechanical particles. And that he found the solutions that are quite unique solutions, such that it's the self-antiparticle as a solution. It turns out this Majorana particle is a formal solution, one of the formal solutions of the Dirac equations, but it's weird in a sense. It's a particle is its own antiparticle, especially if you just think about in terms of the electrons, it's basically half electron. It's a half electron or half hole-like, and they always comes as kind of pair, right? What has been just realized in a rather recent year is if you just realize this Majorana particle pairs, and especially if they are isolate pairs, and if you just can just kind of play around, because they are inherently entangled between these two Majorana particles, and they are rather robust because it's topologically protected. One may be able to use this as the elements that realize robust quantum computing. And out of this idea of the past 5 years, in the condensed matter system, there's a massive search of the material platform to realize these Majorana particles to be used as a quantum computing, right? And there are many examples that I don't want to go through, but some of the a lot of the commonalities, you need some sort of spin-orbit couplings or that just kind of something that twisting the band structures around. And important ingredient is you have to interface with the superconductor to proximatize and realize this half Hall and half electron type of system. There are quite a progress in this field, in the condensed matter field, and just realizing one of the materials. Many topological insulator, it turns out it's also two-dimensional like, and that's kind of good, interesting point. But the other part, interesting part is you can just also work on the non-conventional superconductors, such as the P-wave superconductors and quasi-particles or the vortices in this, the P-wave superconductor, often considered as a Majorana particles. The problem here that is there's another easy way that we can realize those kinds of systems in the reliable way. The one example I want to share in this two-dimensional world, there are many things that kind of touch upon this two-dimensional system, is the last part. It turns out there's a way that you can also proximatize these chiral states of the quantum Hall states or quantum anomalous Hall states and try to realize this robust, the topologically unique particles in there. How it works? Basically, we need to know that how to proximatize the quantum Hall state with the superconductor. And that has been really difficult task in conventional semiconductor system. Part of the reason is when you just apply the magnetic field basically compete with the superconductivity. And furthermore, in typical semiconductor under the magnetic field, it's very difficult to make the good ohmic contact to do just a quantum Hall measurement with the superconductor, which is usually refractory materials. Here comes that kind of interesting new directions. I told you about the graphene, and this is a single layer and a high quality two-dimensional system under the magnetic field. We know that it developed a nice quantum Hall effect. But even further, because it's a zero-gap semiconductor, nevertheless, once you put down the superconductor, there is a good way you can engineer a fairly highly transparent or highly effective superconducting contact in there. So it turns out graphene can be a really good candidate. One can realize both superconductivity proximatizations as well as the quantum Hall effect. Indeed, this experiment, so we made this very narrow, the finger-like the electrode onto the graphene channel and apply the magnetic field. Under the magnetic field, once the Landau level forms and everything's quantized, it turns out the transport is only carried by these edge states. And simply measuring the edge state, the potentials, one know that how the quantization is happening. So basically, we just did very similar experiments like the typical quantum Hall measurement, except that one of the electrode is replaced by this niobium nitride, which is known to be type 2 superconductor, where the HC2 is large enough such that when you have the quantum Hall effect, still the superconductivity can be preserved. In our experiment, we found that, that this sample actually did show that nice quantum Hall effect down to, say, few Tesla, nicely developed all this Venn diagram with all nice quantum Hall plateau. But not only that, when you just carefully measure the chemical potentials of the edge states, we realize the interesting part. Some part of the chemical potential we measure in the circuit turn it to the negative. And that's a very weird moment because we just applied only the positive voltages, 0 to positive voltage in these circuits, but at some point of your circuit, you start to pick up negative voltages. Classically or semi-classically, it cannot be explained. And the way that it happens is when this edge states carry the electron and hit the superconductor, across the superconductor, basically this electron turns into the Hall out of this interesting procedure, what you call the Andreev process, right? And from there, that electron turns into the Hall, leaving the Cooper pair behind, and we start to be able to read these negative voltages in the circuit. And this fact that we just read this negative voltage tells us that there is electron and Hall conversion is happening in this system. And in terms of this more complicated word, this is what you call the Andreev process, or especially cross-Andreev process. And it happens when you have the really thin superconductor where the electron is allowed to turn into the Hall across this very thin superconductor, thinner than the superconducting coherence length. Which means that if you just make the superconducting electrode thicker and thicker, basically we start quickly lose the signal, negative signal. And this length scale tells us about how much actually the superconducting coherence in this system. So it has been nicely done, right? I mean, you may say that, all right, so I can see this one, but why this is related with so-called Majorana particle? Up to here, this is basically nice description of the experiment of this 80s and 90s idea, right? What we have this recent tweak is there's a new way that we can just view this problem. So I'm just kind of showing you that device, but let me just zoom in what does the device look like, right? For a moment, let's forget about this is a superconductor, right? And then quantum Hall edge state comes in. If there's no graphene underneath, indeed we just make the trench out of it, that the quantum Hall edge state will turn around and going like this, right? So across this thin trench that we had, the one quantum Hall edge states run this way and the other one is opposite way. This is basically counter-propagating states. And then we fill that state in between the state with the superconductor, which can couple that these two different edge states, counter-propagating edge states, through the superconducting, superconducting interactions. Basically, this is a basic ingredient of any Majorana physics. Any Majorana particles that you want to create in the previous the material platform works in very similar way. That you have the counter-propagating states topologically protected, right? But then you just couple them with the superconductor, proximatize them. At the end of that, basically at the end of those kind of proximatizations, you just gapped out those kind of the counter-propagating edge states. At the end of this gapped out state, you actually expect to see the localized Majorana. And that's basically modern view. And this is not my idea, my saying that all these theorists actually worked it out, this type of things, coupled with the counter-propagating states. So this is what is the expectation. Interpretation of our cross-Andreev reflection, therefore, is basically there's a resonance state that through this Majorana, that we have the resonance transport through the edge state, which actually turn into the cross-boundary reflections. Why this is exciting? Basically, this is a way that now we can start to see that, how we can engineer the Majorana states and then how to manipulate them in some sense. Rather than we start with the one Majorana that I can demonstrate that we can just have this end, we can make another fingers, and then indeed you can ask, what if that I start kind of turn on the interaction between these two Majorana? Or maybe I can just annihilate or create it. And this is basically the basic ingredient we can just present. Not only you can create the Majorana particle, we can start to the interactions. As you see here, this is extremely preliminary data. We just start to make these things that we at least know that from the cross-boundary reflection, there exists of the Majorana, and we start to just pick up the idea that we can create them, we can manipulate them. Very preliminary data, but promising data is indeed when you just measure the Josephson coupling between these two through the Majorana, we start to see that whenever we change this quantum plateau, we start to see that this Josephson critical current changes with same steps that we expected from this the superconducting gap, indicating that these two states are closely linked together, and hope that just give us the promise or hope that we must be able to manipulate them more efficiently. So at this point, this is extremely preliminary data, but already I give you some flavor that just combining that advantage we have in this two-dimensional system such that we can create this clean system. We can also make the contact, proximitize with superconductors. I give you some flavor that what kind of non-conventional device we can create, right? As you see in the title that I mentioned also, it's not only electronic device, but we can just go for the optoelectronic devices. So let me just kind of dwell a little bit on this now optics side. Well, I'm not this really optics guy. I know that I'm in danger that in this institute I'm talking about the optics, but let me just try to do that anyway. So in my simple mind, that the important object that we have to discuss when we just discuss of the optics, the optical properties, optoelectronic property in semiconductor, it's excitons, which is basically one can create in this field band with gapped system of semiconductor shining the light, and we know the photon can create the electron-hole pair as excitation, right? Well, this electron hole can coulomically interact each other, and they can form the bound states. So that's what we call the excitons. And this bound state shows a lot of the interesting properties, like the Rydberg excitons is a good example, but absorption properties and a lot of the optical properties governed by this exciton. Now, unfortunately, this exciton is rather short-lived because it's not the ground state, it's a transient state. So depends on the system, exciton lifetime can be something like even less than picoseconds to something like the microseconds. Depends on the all this the mechanism how the exciton is recombined back, right? But you can ask the following questions. Well, exciton as a composite particle, they must have, if I just treat like the quantum particle, should have some symmetry. What is their symmetry? Well, it's pair of the electron and hole, which is both of the fermion is spin of the 1/2. So exciton must have the integer spin, which means that we know that this is supposed to be boson, composite boson. So idea is, well, if the exciton is boson, if I pump a lot of excitons, then in principle, they can condense down into the Bose-Einstein condensation and form some of the macroscopic quantum states. Maybe that can be cool that one can use something. Only the problem is exciton is rather short-lived. So the first thing you have to do to move in that direction is just to try to create the long-lived excitons. One part we can do is you can just work on this semiconductor quantum well. This is something that Professor Na-Young Kim has been working on for a long time, right? You just create this quantum well, and then nice thing about this quantum well, especially in the double quantum well, is you can create the exciton in the one over this well, but also you can apply the electric field, and you can tilt this quantum well, and such that that now the valence band bottom and the conduction band top, also conduction band bottom and the valence band top, getting close to each other such that exciton can be now addressed in the even just ground state in principle, or close to ground state, right? And this idea of the creating this spatially indirect exciton, interlay exciton has been around, and people actually using this type of the spatially indirect excitons, or maybe put these excitons into the cavity to create the exciton polariton in whatever way, that there's been some demonstration you can create this the collection of the exciton, and there's signatures that this exciton start forms at least some collective states. such as spontaneous coherence, actually start to appear. Some of the examples that recently demonstrated in this semiconductor heterostructures. But nevertheless, exciton in this semiconductor is still not a ground state, such that it can be only transient and only exists in the pumped the system, non-equilibrium states. So whether this, you can call this exciton condensation or not, that's a lot of the debates in the system. Now, there is a way that though, one can make this exciton as a ground state, and there's a possibility that you can condense them. And it's going back to, again, quantum Hall system. So the idea is following. Imagine that I have the two quantum Hall system, then just one top and bottom each other, and apply the magnetic field in there, right? If I just feel this, then there's a Landau level forms, nicely Landau level formed. But let's imagine that instead of that, I make that this two Landau levels completely full or completely empty, where you expect to quantize Hall effect appears. What if that I just partially fill this Landau level? And partially filled Landau level is kind of bad metal. I mean, nothing special things happen. It's just kind of poor metal, right? But nevertheless, if you just put these two partially filled Landau level very close to each other, and then I just kind of deliberately put this the density of each of the layer. Each of the layers partially filled, but it's complementary partially filled means that if I just put them together, they're full Landau level. And in this particular case, especially when the layers close by, then you naturally expect that electron in the top start to see that electron in the bottom layer. And of course, the exchange interactions or Pauli exclusion principle tells us they don't want to sit in the same space. They just kind of want to expel each other, such that you want to make this Pauli exclusion principle works. Which means that as they put the layers close by, they just self-organize such that they just avoid each other, right? Now, if you just look at this system from the top, it looks like something like this, right? If you just project it out, it's completely full Landau level, right? As if they behave like completely full Landau level. So that's basically the idea behind of these things, that you have the partially filled two Landau levels together and put them together, and then you just form this completely full Landau level. Why this is related with exciton? If you just go back to this picture, basically here's the electron directly related Hall and electron directly related Hall, such that you start to see that this exciton pairs actually forms in this picture, right? But as a whole, this is a full Landau level, which means that as a whole, they actually restore back the quantum Hall effect, as if these two layers behave as one layer, right? And these beautiful arguments actually worked it out already in gallium arsenide. And from the 90s, that Jim Eisenstein's group at Caltech is basically the pioneer under this field, demonstrate that when you have these two quantum Hall layers together, they start kind of talk to each other and form these quantum mechanically coherent states. Can be detected by just carefully measuring the transport. For example, now again, you have the two layer that you send the current in the top layer and just measure the voltage in the bottom layer and define the resistance. This is not the direct resistance. This is what we call the drag resistance. And they start to see that drag resistance is quantized. I mean, if these two layers doesn't talk to each other, there's no reason they are connected to each other. But in this picture, basically because of this quantum mechanical process, they are connected. And they do see that there's a drag resistance appears, and this drag resistance is also quantized, and that has been strong evidence that in these two layers just kind of talking together and make this exciton, and not only make the exciton, they actually condensate it into the quantum mechanical system, showing this quantized drag resistance. So this has been beautifully done in past 20 years and well demonstrated. Now, of course, in the two-dimensional electron systems, such as graphene, boron nitride, all of these things, as long as your layer is clean, you can repeat this one into the graphene, right? Well, here is the devices. So we have the two graphene layers separated by the boron nitride with the top and bottom gates, and each of the layers got contact. As I mentioned, that this can be done. And then you just kind of, the real device image is like this. And then when you apply the magnetic field and measure their drag resistance, indeed, we do see that, like what in gallium arsenide, we do see that drag resistance is quantized, right? So quantum Hall effect appears in one layer to the other layers is kind of connected, although electrically they are separated out, right? So two partially filled Landau levels shows a drag quantum quantization, indicating indeed that we are seeing the condensed magnetic exciton in the system, right? Well, on the top of that, since we have this more capability onto the tuning the density, the gallium arsenide people did see in the half-field Landau level, but in this case, we see that those effects into the many different Landau level. For example, 2.5-field Landau level to the half-field Landau level. We do see again very similar drag effect, showing that we can also create the external condensation in various places of the different different Landau level. But perhaps the very different things that we cannot see in the gallium arsenide, but clearly see in this particular system is the following case. I told you that in the magneto-extern condensation is very close to the extern condensation, except that as a whole layer, it is still quantum Hall effect such that we have the edge state do exist, right? But in principle, we can make this rather than this coupling between electron Landau level to another electron Landau level in different layer. What if I just using the gate that turn this on the bottom layer of the graphene into the whole system, right? So I have the electron Landau level to the whole Landau level and ask the same thing. Now in this particular case, it is a real hole and there is a real electron and still this is a real extern forms, right? But the important idea there is, especially if you just put the same amount of this the Landau level filling, so half-field Landau level, half-field Landau level, and their edge states or their edge state, the edge state is counterpoint in the opposite directions, meaning that this becomes an exciton, but real insulator without any edge states. It's very close to the real extern condensation we are creating if you just kind of put the electron and hole together and make these things. Indeed, our experiment I showed you, we can just choose now electron and hole side. So especially this is the filling fraction of the top layer, filling fraction of the bottom layer. Along this line, basically we populate half-field Landau level top and half-field electron Landau level top, half-field whole Landau level in bottom, right? What is the feature we are seeing is all this, the drag resistance and drag conductance we are measuring goes to zero. Basically, it becomes really good insulator. And if you just can simply measure two terminal resistance all together, it turns out your conductance actually dropped to zero when you have this half-field Landau levels together. And this is rather weird situation. So I know that this is already esoteric, but let me just kind of explain that something really simple. Half-field Landau level, I told you, is a bad metal, right? So I have the electron half-field Landau level, bad metal, electron whole half-field Landau level, which is bad metal, right? So you have the bad metal, but it's still metal, conductor. What if you just put them together, you make the parallel plates, and you just kind of measure them together? What is your expectation? Classically, okay, it's a poor conductor, another poor conductor. It is probably still poor conductor, but slightly better conductor, right? What I'm saying here is, if I just add the two conductors together, but suddenly it becomes insulator, although it's parallelly connected. And why is that? Because it's an electron and hole coupled together. When I just try to send the current, electron is flowing that way. If it is strongly coupled, hole is all flowing the same way, it cancels the current, right? So that's why it becomes an insulator. Another way to say that is now the carrier that here is basically electron-hole pair. It's a neutral object. They cannot carry the current anymore, right? So this is basically a clear demonstration, but something really happened when we have the really just extern condensation here. A little bit more of the exciting part is the other way that you can view that is now I send the current in the bottom layer, but simply that measuring the voltage in top layer. Oh, sorry, that I'm just bias the voltage onto the top layer, send the current on the top. But if I just make the short in the bottom layer, what happens is in the bottom layer there is no voltage source, but then you start to see the current is flowing. Another way to say that is, well, extern is here. If the extern is dragged by this the bias voltage in the top, basically if the hole is flowing there, electron is flowing there. In other words, current should be flowing there. Amount of current I'm getting here should be same as amount of current there. Indeed, if you measure in this situation across here that where extern is condensating, exactly we're getting this dragging current is the same as a driving current. It's what you call the perfect drag, right? And this is another indication. Indeed, we have the condensed extern in this system, right? Now, we can just do a little bit more things. I don't want to kind of dwell on this one a little bit more, but you can actually carefully look at this, how this extern condensation is happening in different magnetic field and different temperatures. And in all of indication, let me just skip this one because it's Okay, so I will do it here. Then you start to see that there's an interesting the phase diagram I can draw that how the extern is condensating as a function of magnetic field and temperature. I don't want to go into too much of detail, but once we see these things, we just realize this is not only just what we are seeing in the experiment, but it has been discussed in a long time in extern condensation communities. It's basically that phase diagram you expect to see. When you have the excitons in electron hole, of course, if the temperature becomes high and high, exciton becomes unbinding and then becomes electron hole plasma. Or if you just put more and more exciton in there, there's so-called Mott transitions happen. In other words, that basically screening between the charge carrier increases such that you start to lose the Coulomb binding energy, that the electron hole, the exciton system, turn into the electron hole liquid, just kind of unbinding states, right? And all of this system, as you go down to low temperature, they can condense. Of course, if you have the exciton is boson, it condensed into the Bose-Einstein condensation. If you have the electron hole plasma that condense as a superconducting state, BCS, turns out that in the low temperature, there should be some BC to the BCS crossover happens, and that is what is the expectation. Indeed, what we measure into our system is very analogous. When we just measured, we are seeing the very similar things happening. Let me show this part. When you look at this gap that out of our measurement, we are seeing that this condensation gap or transition temperature shows nice dome shapes, and that kind of exact the crossover what we expect to see in the BC and BCS. So indeed, this system that we just create out of these magnetic excitons really follow through what we're supposed to see in this exciton state. However, as I mentioned, that I want to talk about the optical states, but you already start to see that this guy is already digressed of his convenient the phase space of the graphene, not to mention about any optical properties, right? I mean, this is a nice demonstration of exciton condensation, but only appears in the strong magnetic field, right? How about the real excitons? 2D system we are dealing with actually is a good system. In principle that we can discuss about exciton. Part of the reason is in 2D semiconductor TMDC, it has a decent gap, and because of its thin atomic limits, when you shine the lights, they form the excitons, but they tend to have the very strong binding energies simply because electron hole pair you created, all of the field line going out of the materials without screening, and their Coulomb interaction becomes very strong. So it turns out experimentally you find that half electron volt of this exciton binding energies. Because of they have the strong binding energy, in principle you can also attach this exciton with a charged particle, create so-called trion or positive or negative charged trion states. They can be also stabilized. And this type of the beautiful idea has been tested out already in the two-dimensional electron system by the many other groups. Here is the Tony Heinz group and Xiaodong Xu's group. They all demonstrate indeed exciton do exist in two-dimensional system. They are very robust and strongly bound. And you can create a lot of different type of optical species and make the interesting coherence. And interesting another part is strong spin-orbit coupling in the system make this valleys got spin split, which means that using the light, you can also control the spin state of these particles or excitons in the system. So we know that this is a very exciting system. Can we actually couple this with electronic device? Indeed, it's a relatively straightforward, right? You just make this a transistor. I just showed that before, right? And then you just put the gates as if it is field effective transistors. Rather than you just measure transport, you can just measure the optical spectrum and see how it looks like under all these kind of different electronic conditions. So here's a good example. Here is we have a transistor made of the tungsten diselenide monolayers. We have top and bottom gates, as you will see the Y, and the source and drain, and we can just just study about their transport properties. But we can also study their optical properties as a function of a gate. Using the gate, we can control the electric field as well as the charge density. And this particular diagram I'm showing you, that's a photoluminescent data. As a function of the density, we can change in the system. If we just apply the same polarity of the voltage onto the gate, we can change the density without applying the electric field. Or we just apply the different polarity on top and bottom gate, we can change the electric field without changing the density. And what you see here is their spectrum. The bright, the red is basically peak, and blue is the deep, And there's a peaks appears in the optical spectrum. We can assign following through the previous work. This is exciton. This is negatively charged trion. This is positively charged trions. As a function of the density, exciton quickly dies off outside of the gap region. The energy got shifted as you change the density because their screening property got changes. So we start to see that that spectrum got changes. But important part is this exciton we create or trion we create in two-dimensional system. As a function of the electric field in the vertical directions, the intensity got modulated, but what you see in the energy position is that just constant, right? And this tells us whatever dipole moment of this species, excitons or trion we create, this dipole moment should be in plane, such that it's orthogonal to the electric field we applied in the vertical direction. Another way to say that is as a truly two-dimensional object we can create, optically create it, and potentially we can also electrically manipulate it, right? While this the two-dimensional system we create is a completely the two-dimensional electron the system, one can create this the rather semi-three-dimensional system by heterostructuring. I told you that we can create the p-n junctions by just kind of choosing different type of materials. In this particular case, molybdenum disulfide, tungsten diselenide, put them together. It's a type 2 band alignment. We can create this, the structures. I showed you before that this behaves like p-n diode. We can create the photoluminescence, and we can get the electroluminescence and photocurrents out of it. We can actually put a little bit more efforts in here. We can put complete control, top and bottom gates, each of the electrode in each of the layer, and if each of the electrode need to be gated to make the ohmic contact. But in the end of the day, we have the device. By the way, this is kind of heroic efforts of the couple of students, and making this type of device takes some time to build in the working device. But nevertheless, once you make the device, you get the beautiful optical spectrum. Here I'm showing you again photoluminescent curve. So this one is that when we have the tungsten diselenide alone, this is where the molybdenum diselenide alone in low temperature, the peak width is about millielectric volt, almost a radiative lifetime they're limited. But the interesting part is interlay exciton. When you have this part of this, the transitions, we do see that the peak appears in heterostructure area, indicating that indeed now we have this interlay exciton forms. And that's an important kind of beginning point, right? I told you that interlay exciton can be long-lived in principle because now electron holes are separated, right? And on the top of that, because of this band alignment is not the three-dimensional structures, by just a gate, we can control this band alignment, which means that this energy scale got changed. Indeed, that's the case. When we actually show this interlay exciton peak changes with the gate voltages, again, as you change the density, we see the interlay exciton energy got slightly changes, but outside the gap, we quickly lose the interlay exciton. So interlay exciton only appears when Fermi level is within the gap. But the important part is, unlike this two-dimensional system, in this p-n junctions, in the atomically thin p-n junction, as you change the electric field by controlling the gate, interlay exciton energy is linearly changing, just kind of linear stock shift, meaning that dipole moment is now out of plane. And just looking at this magnitude of linear shift, we know that this is a completely interlay exciton we just created. Now, I told you interlay exciton can be long-lived. Indeed, if you just look at the exciton lifetime is reasonably long. It's something like 200 nanoseconds to half microseconds. More importantly, as you just change the gate voltage, as you just apply the electric field along the exciton direction, such that you start to pull these exitons away, you start to get this electron and hole wave functions overlap and less, and you expect the lifetime becomes longer and longer. And that's precisely what you see. As you apply the electric field, lifetime becomes longer because you pull these exitons out, right? And such a long-lived exciton is already first ingredient we need to create the exciton condensation, right? The first things you start to see is this, because the exciton is long-lived, when you just create the exciton, they can start to kind of diffuse out the sample rather fast, right? In this 10 micron size of sample, you just kind of shine the laser there about this spot, and then you start to see that the exciton can be picked up all across the sample. Even further, you can actually look at this, how the exciton get diffused out by just pulsing this exciton, and you can get this exciton actually diffuse out rather fast, and just the time dependence, this exciton measurement, we can start to get this the numbers. It turns out diffusion constant of exciton is 3 centimeter square centimeter seconds, which actually correspond this the mobility of the carrier that we measure in the system. So we know that it works. More important part is that this inhomogeneity that start to tells us the exciton we create can be also trapped in some part of sample due to the inhomogeneity, and the density inside of trap can be controlled by just sending the current through the system, one of the layer. So this start to tells us that in principle, using the current in one of the layer, we may be able to drive this excitons in the system. This is very analogous to the magnetic exciton I showed you, right? When I send the current in one of the layer, then I start to get the perfect drags into the another current. Unfortunately, we are not in get that range of the measurement, but clearly the optical spectrum start to tells us that sending the current in one of the layer apparently affected systems in the way that exciton distribution is something. So it's a very kind of important part. Are we in the exciton condensation regime? I think, let me just skip this one. I think we probably not. We don't have the really good evidence yet, but at least we are getting it there. How do we know? If we just pumped in the excitons with high density, the exciton energy start to blue shift, and that's because of exciton-exciton interactions. And this blue shift actually gives us a sense that what is the exciton density we can create in the system without heating the system. It turns out the exciton density we're creating about 10 to the 10 to the 11 centimeters. We don't know that yet, that what is the density that exciton can be created. But if you just rely on the mean field type of the theory, calculations are already here. Okay, so this is a BKT line where the exciton condensation, BC condensation is happening. So VI is about here, right? And then you see the temperature is something like this. We measure this as 4 Kelvin. So in terms of this density, we are not really far from this mean field, the line of the exciton condensation. We hope that once we just create a little bit more careful experiment, especially direct type of the experiment, we should be able to really pick up this quantitative analysis of this, the exciton condensation features. So this is another example. I think at this point, it is just the demonstrations of that. At least we start to see the very first step, that what we are looking for, that just kind of beyond the conventional optoelectron device, such as the photodiode or the photovoltaic device. And here's another example, that once you create this kind of exciton condensation, in principle, you can create exciton condensation even a really elevated temperature, as long as you just make the long-lived excitons in this system. And that's kind of another hope, that maybe there's a way that we can create these quantum electro-optical devices based on this type of the van der Waals heterostructures. The technology got evolved. Not only you just kind of create the excitons, but you can create these excitons, and they can one can modulate the exciton in the various positions and some things. I don't have the real times going through, and just kind of create this some of the localized excitons and trions by just the engineering. The important part is, important message that I want to deliver in some sense as a summary is this the new opportunity that we just received, just arises from this availability of the various different type of materials, combined with this the mesoscopic experimental technique, start to at least give us some of the exciting the new quantum physics, especially new many-body quantum physics, start to appear in this type of system. Now, the next level question is there a way that we can tame this type of new physical phenomena into the kind of device going beyond of the CMOS type of applications? So that's basically next many years of the answer that we have to work on. Finally, I should probably thank my group first that they just kind of make all this, the various part of the presentation is possible, but also not only is within my group, there are strong collaborations, both the superconducting side, optics side, and theory side, that most of my local collaborators, as well as my collaborator in Japan, who provide high quality of this boron nitride crystal. Thank you very much.